What's up, guys? It's Mr. Brengle, and today we're going to be talking about Ohm's law, and involves voltage, current, and resistance to begin our discussion here on circuits. So, what I've opened up here is a circuit simulation from fetcolorado.edu. You can see the URL up here if you'd like to go try this out yourself, but you can simply type in circuit FET on Google, and this will pop up. So, um, first, let's talk about what these things are, and then we'll kind of talk about how they affect one another, and we'll look at the circuit and everything. But voltage is similar to, so I'm going to use some analogies here. I want you to think about at home, if you've ever taken a vacation or something like that, and you get in the shower and there's low water pressure. And the water just trickles out of the shower, and it's just a terrible experience to take a shower like that, right? You want high water pressure so that the water comes out nice and with a good flow, right? So current is like the water in your pipes. Okay, current is the flow of electrons, so you can actually see them right here. These are electrons that are already found in all objects and in this wire. And they're moving here. So when the electrons are moving, that is called current. Okay. And the reason why they move is because of voltage. Voltage is the equivalent of water pressure. So in the analogy, so the voltage is the electric pressure that pushes the current or the electrons through the wire. Okay, so if you have a low voltage or a low electric pressure, then the electrons are going to trickle through the wire. And if you have a high voltage, high electric pressure, then it'll push them through quickly. Now, that is somewhat dependent then on the resistance of the wire. So in your pipes, you might have like a smaller pipe or something clogs up your pipes, and then the water doesn't flow as well. Resistance is just the opposition to the flow of electrons, and resistance is found in all materials. So anything that you put into a circuit will have resistance. So the example I've used here is a light bulb. You put a light bulb into a circuit, it's going to have resistance. And the more light bulbs you put in, the dimmer that light is going to get, okay, because it's trying to support multiple light bulbs instead of one. Now, let's kind of talk about Ohm's law. Ohm is a famous scientist that came up with some of this stuff. And Ohm's law states that the voltage and the current are directly proportional, but that current and resistance are inversely proportional. And if I rearrange this equation here, we can rearrange it a couple ways. We can go for current. Current is equal to voltage divided by resistance. Or we could solve for resistance, which is equal to voltage divided by current. Okay, so the point here is that current and voltage here are directly proportional to one another, meaning that if I increase the voltage and leave the resistance the same, the current will also increase. Okay, so let's show an example of that here. So if I can actually change the voltage of this battery. Okay, I want you to watch the flow of electrons here, and I have this thing down here called an ammeter that's reading the current, and right now it's measured at 0.9 amps. Okay, so that's what we measure current in, is 0.9 amps there, otherwise known as amperes. Okay, but most people refer to them as amps. And then I have a 9-volt battery. So you measure voltage in volts, which is quite simple. But let's go ahead and increase the voltage, and let's watch the current value here and see what happens. So you can see as I increase this voltage and I can slide it way high up, that current is increasing. Notice that that light bulb gets brighter and brighter. The more current that's flowing through it, now it's moving super fast, right? The more current that moves through there, the brighter that light bulb gets. So as I increase the voltage, which is now up at 61 volts, I have a larger current than where we started. It started at 0.9 because we had a 9-volt battery. Okay, so current and voltage are directly proportional. If the voltage goes up, the current goes up. The voltage goes down, the current goes down, assuming we keep the resistance the same. Okay, now um, on the flip side of that, you've got the current and the resistance here. Resistance is in the denominator of that equation. So that means it's going to be inversely proportional to the current. So, and that should make sense, right? The more resistance you have, the less current you're going to get. And if you have less resistance, then the current should flow easily, right? The electrons have the ability to flow. So now if I change the resistance, so let's increase the resistance and let's watch that value on the current. So if I increase from 10 ohms to say 67 ohms, which is what we measure resistance in, this funny little symbol here is the Greek letter omega. It stands for ohms, which again is that famous scientist. But notice that the current went from 0.9 down to 0.13. So again, if I continue to increase the resistance, that current continues to go down, and you can actually see that the electrons in this wire are not moving very much. They're moving very, very slow. But then if I continue to decrease that resistance, you see the current gets higher and the light bulb gets brighter. And if I go all the way down to zero, well, then it lights my circuit on fire. So we'll go ahead and we'll go back down to about 10 ohms here and go back to where we started. So you can see there that resistance and current have an inverse relationship. Okay. And that's true even if we look at the other equation over here. Notice that resistance, even though we're solving for resistance, current ends up being in the denominator there. So now, kind of covered what we measure all these things in. So voltage measured in volts, current measured in amps, resistance measured in ohms. We've talked about the relationship that they each have on each other. Current and voltage are directly proportional. If I increase the voltage then and leave the resistance the same, the current will increase. And if I decrease the voltage, the current will decrease. And then current and resistance are inversely proportional, meaning that the higher the resistance, the lower the current, and vice versa. Okay. We will, just for purposes here, I'm going to add in one more light bulb just to show you that by adding in another light bulb, we're adding more resistance to the circuit. So I'm adding another 10 ohm light bulb. And when I add that in, notice that the current has decreased again. So the more light bulbs you put in here, the more resistance there is, the less current flow we'll get. And eventually we'd have to increase the voltage of the battery to make sure that we have enough current to support all the light bulbs. So we'll do a separate video where we talk about different types of circuits, series and parallel circuits, and how those work. But for now, this is a good start on just understanding what these things are. Just as a reminder, try to think about that analogy. The voltage is like water pressure, except it's electric pressure that pushes the water or the electrons through the pipes or the wire. And the current is analogous to that water flow. And then any sort of obstructions would be considered resistance, and anything that's in the way of the electrons that it has to go through, that's going to have some resistance. So make sure to let me know if you have any questions about any of these topics, and we'll continue talking about them in class.